welcome back to Project PhoboCam. In this, the second week of the project, I'm going to be focusing on the design and construction of a device called the Desiccator. This will remove the water that's present in the samples of Martian analogue clay that I prepared last week, and I might prepare some more samples later on this week. Basically, it will be an aluminium container which we can attach a pump to it, suck out all of the Earth's atmosphere inside of it, and either leave it as a vacuum or put in a dry nitrogen atmosphere inside of there, not containing any water. At the bottom of the box will be some kind of heating element. For example, very similar to the kind of disc that you see on top of just a usual domestic cooker, for example. This will heat up the clay samples to around 200 degrees Celsius in order to evaporate all of the water that's present inside of the clays. We can then pump out the water, leave it for about 3 to 4 days, and then we will have our samples ready for the scientific analysis that will follow. So I've been doing a bit of shopping and looking about at the different options online. So I'm just going to go and submit the order, send that over to my supervisor. Looks like it will cost just short of around £300 or so. So we'll get that forwarded over to the physics department and basically wait for it to arrive. Should be about next day delivery, so then hopefully we can start building it. Well, until then, I think I'll go down to the lab and finish preparing that sample from last week.
At the end of day 6, 2/3 of the 4th sample have been prepared. Well, that's one way to increase productivity. At the end of day 7, sample 4 is finished. Okay, it's day 8, and whilst I'm waiting for the heating elements to arrive to start construction on the Desiccator, I thought it would be nice to show you some of the other things that we do around Oxford. This is the observatory for the Space and Astronomy Society here at Oxford University, and I want to take you on a quick tour around it and show you what it's like. So, James, if you can come in here. So this is James, he's also another member of the Space and Astronomy Society. So let's go inside. So James, so why don't you tell us a little bit about the telescope itself?
So the telescope we've got here is a Anisotropic cascgrain. What happens is the light comes in through this here aperture, and it comes through and reflects off a huge mirror at the back here, and it gets reflected off another mirror at the front and finally reaches the eye through the eyepiece, which is attached here. And it's mounted on what we call an equatorial mount. So it rotates about this axis and also about this axis, enabling us to see pretty much wherever in the sky the trees allow us to.
Yes, and if we want to look somewhere else, for example, we can swivel the dome around.
We can indeed. Anything up? Lost the moon.
Yeah, the moon's up there somewhere. And of course we have gears that now allow us to compensate for the rotation of the Earth if we want to zoom in really far on a certain astronomical object.
So of course, due to the rotation of the Earth, an image will move across the field of view of the telescope. So to compensate for that, we have these drives, which we can switch on and off. These are the actual machines that rotate the mount, and using that we can have the object in the field of view for as long as we like to allow lots of people to look at it.
Yeah, so speaking about looking, so why don't you show us some of the lenses that we have, depending on whether we want to zoom really far to do in detailed studies or just get a general overview of the object.
Yes, that's really important actually. So here we can have our largest eyepiece, as you can see. Let me just take the lens caps off. Now you see here, there's quite a large opening there. So this is quite a large field of view eyepiece, allowing us to see quite a lot of area of sky through the telescope. If we compare it to our other eyepieces, this one's progressively smaller, and this one's smaller still. This is the highest magnification lens, and this is the lowest magnification lens. Of course, the trade-off is you see less sky through the high magnification lens than you do through the low one. So if you want to look for diffuse nebulae or comets, you use the low magnification lens, and if you want to look, say, in detail of planets, you use this one.
After that nice trip to the observatory, it's over halfway through the week, which means it's time for our weekly scientist feature.
Hi, I'm Dr. Sean Lindsay, and I'm happy to be talking to you today a little bit about my research. So what I do is I research the very smallest things in the solar system, the small bodies as we call them. And these are things like comets, which are beautiful night sky objects, of course, and everybody loves them whenever they come and visit Earth, and asteroids. And really what I'm trying to do by studying these objects is I'm using a type of analysis called spectroscopy. And what that does is it breaks up light into its component wavelengths, and depending on what kind of things are making up these comets and asteroids, you can actually look at these spectra and find distinct diagnostic features in them that tell you, like, oh, this one's made out of the mineral olivine versus this one's made out of the mineral pyroxene. Or you can even do things like elemental analysis and things like that. But I focus on really what are the small bodies, what is the physical makeup, so what is their rock structure. And the point of this is, if we want to understand how our solar system formed, then what we really need to do is have a list of the ingredients that went in to forming a solar system, and then we need to know what the end products look like now. We actually have access to the end products now, the comets and the asteroids, but by going in and learning what they're made out of, we can then start to get an idea of the physical processes and what kind of physics actually happened that went from basically just this giant cloud of gas and dust that then collapsed under its own gravity and formed itself into a disk, and then built these small bodies, which then went into building the planets. So if we want to study how the solar system actually forms, going towards these small bodies is the first and primary source of evidence. So that's what I do. I try to figure out what the comets and asteroids are made out of. I'm mostly interested in comets, so I've been very excited about 67P Churyumov-Gerasimenko with the Rosetta mission, one of the most fascinating missions that's happened, I think, in decades, because we're now visiting one of these small bodies for the first time up close. We're seeing not only what the surface structure is in a very detailed way, since Rosetta is in orbit around it, but we also sent that lander, Philae, down to the surface, which has given us wonderful evidence about not only what kind of rock types are there, what are the minerals there, but we're seeing complex organics, we're seeing ices, everything that we expected to see is there. But we've only seen bits of pieces through surveys of lots of comets. Seems like 67P is showing us that it has everything that we would have expected, which is absolutely phenomenal.
It's day 9, and you know, whilst I was just walking through the lab earlier, I saw an interesting transparent Perspex box up on one of the shelves over there. And that gave me an idea about how we might want to do something slightly differently for the Desiccator, because I can see a distinct advantage from being able to actually see what's happening inside of the sample chamber, instead of just using, say, an aluminium box like we were originally considering. So we're still waiting for the heating element itself to arrive, but in the meantime I've been looking at some design work and sourcing some components that we could use. So now I'm just going to demonstrate to you the general idea of how the Desiccator will function when we build it next week. So here I have a balance, which is to simulate the heating pad that we're going to be acquiring hopefully tomorrow, but at the very least next week. And then what we do is we will take a sample cup, we will load one of the clay samples into it, place it on top of the pad, and heat it up to around 200 or so degrees Celsius. Then what we do is we take a transparent box made of acrylic or Perspex, which will then be placed over the top, like so, and the real one will probably be about the same size but slightly larger in some dimensions. So, wired up to the outside of this box, we will have some electronics, because there's going to be 2 sensors inside of the box. One measuring the humidity, or how much water is inside the nitrogen inside of it, and the other one measuring the temperature inside of it. Because the problem is that the melting point of an acrylic box such as what I'll be using is around 160 degrees Celsius. So we need to make sure that the temperature isn't going too high, otherwise the entire box is going to melt. So in addition to the sensor, what we will also have is an airflow tube connected up to an external nitrogen tank, which I can control how much of the nitrogen per minute is flowing through it. And we need to make sure that we set the rate just right so that the air inside of the box doesn't get too hot. Otherwise, as I said, it will melt. But that's an outstanding question, and I'll probably try and do the theoretical calculation for that rate tomorrow, actually. So this is the general principle. So let's go out and look for some components to buy. So let's go shopping for the rest of the components for the Desiccator. We've already ordered the hot plate, as you can see here, with some of its schematics. The next item will be the acrylic box that it will be going inside. We also need to make this box airtight, so we're going to use some thin strips of pour-on film. Luckily we already have some of that in the lab, which you can see here. The pour-on film will then be attached to the bottom of the box by some adhesive or super glue, which we're also buying. There will also be two sensors, this one measuring the humidity and this one measuring the temperature inside of the acrylic box. In order to connect the nitrogen supply from the tank, we'll need a number of nylon tubes such as these ones, and we'll be connecting the nylon tubes together using push fittings just like these ones. And finally, we'll need some strip board in order to connect and wire together all the electronics. So overall, this is our shopping list. It's day 10 and the hot plate arrived early today, but it's going through electrical safety testing at the moment, so I won't be able to access it till Monday. So in the meantime, I've decided to do a quick calculation which will let me complete the grand design for the Desiccator. Specifically, what I want to know is what flow rate of nitrogen from the nitrogen cylinder into the Desiccator is necessary so that the box doesn't get too hot and melt all over the table and probably end up scolding me. And after I've worked out what that minimum flow rate has to be, I then want to work out how long a single one of these nitrogen cylinders can last for, because the last thing that we want is me to go home at the end of a day, leaving the experiment running overnight, and then the nitrogen runs out, and then water from the air just seeps back in again and wrecks the whole experiment. So that's what I want to calculate now. So I won't go through the full calculation with you because it's quite in-depth, but what I have basically is a differential equation for the energy transfer. This is the fundamental equation that I need to be able to solve in order to tackle the problem. This here is the rate of change of the energy being given to the nitrogen inside of the container. And so you can think of this intuitively as this here is the energy that the hot plate is pumping into the system. But we also have gas leaving the system because of the flow rate. So this second term here is a loss in the energy due to the gas leaving the system. So this is loss and this is gain. And there's then a quite long calculation in order to solve this differential equation, in order to work out what the temperature as a function of time looks like. So I'm just going to demonstrate for you what this function actually looks like, what it means. When we start off, and we've just started heating our sample, here we have time on the x-axis, and temperature on the y, will be at time equals 0, and the temperature will be the temperature of the gas inside of the cylinder, which I've called T0. This is 15 degrees Celsius. And then, when time tends to infinity, e to the minus infinity is 0, so this term dies, and I'm just left with the value T infinity, which will be up here. And the function will look a little bit like it's an asymptotic relationship, so it will go up and then gradually increase towards T infinity. And what I need to make sure is that whatever this value is, this T infinity, it cannot be greater than the melting point of acrylic, otherwise the box gets destroyed. So when you follow through the full mathematics of solving the differential equation, I find that the expression for T infinity is given by the rate of change of mass leaving the system times by the heat capacity of nitrogen times by T0 plus H, where this is the heat transfer coefficient of nitrogen, times by the area of the base plate, times by the temperature of the plate itself, divided by H times A plus the mass transfer rate times the heat capacity of nitrogen. And the great thing is that you can invert this relationship in order to find what the mass transfer rate is, how much mass you are pumping into and out of the system per unit time. And when you do that, you get a relatively simple expression actually. HA divided by the heat capacity times by T infinity minus temperature of the plate divided by T naught minus T infinity. Right, so this is the mass that is leaving the system per unit time, per second, but what I want to know for the flow rate is the volume that's leaving the system per second. So to get the flow rate, what you do is you take the mass rate, you multiply by the molar volume, so that is how much volume there is per mole of nitrogen, so it's around 24 times by 10 to the minus 3 cubic meters per mole, and you then divide by the relative atomic mass of nitrogen. Right. And so when you do that, what do we get when we actually sub in numbers into this? I find that we need to ensure that the flow rate of nitrogen into and out of our system is greater than 2 times by 10 to the minus 4 litres, which is also the same as meters cubed, litres per minute. So we have to make sure that we have more nitrogen than this coming through. So this is good, because that is quite small, and I will note as well that for this calculation, I assumed that T infinity was never going to raise above 50 degrees Celsius to give plenty of margin for safety. So that's the first question answered for what the flow rate that I get to control with this flow meter here needs to be greater than. That is the flow meter up there, so I can control the flow rate. But the next question is, how long can a single cylinder of nitrogen last if we use this flow rate? If we just write the ideal gas law, PV is equal N, well, that's the number of moles, times by the universal gas constant, times by the temperature. Now, inside of the cylinder, the pressure is 230 bars, which is equal to 23 million pascals. The volume of a single one of these canisters, if we look it up on the supplier's website, is 9.78 cubic meters. The universal gas constant, as always, is about 8.3. Well, 8.314 joules per mole per Kelvin. And the temperature of the gas that's coming in is around 15 degrees Celsius, which is equal to 288.15 Kelvin. Okay, so we can rearrange this to get what the number of moles in the cylinder is. So the number of moles will just be the pressure times by the volume divided by R times T. And if you sub in all the numbers, you find we have 94,000 moles. Quite a large amount, actually. So now, in order to work out the total volume that we have of nitrogen available to cycle through our system, we have to take into account the fact that inside of the box we have just 1 atmosphere of pressure instead of the high pressure inside of here. So when the gas comes out of the cylinder, it expands and the volume becomes much greater. So to work that out, what we do is the total volume of nitrogen that we have available to us will be equal to the volume per mole under standard conditions. So that's the volume per mole times by the number of moles here. This value here, under the conditions of 15 degrees Celsius and 1 atmosphere of pressure, is around 24 times by 10 to the minus 3 cubic meters per mole. And if we sub in 94,000 moles into this expression here, then we find that the total volume that we have available is 2,250 cubic meters. So finally, to answer the last question that we have for how long until a cylinder runs out, which is called the burn time, the burn time will be given by the total volume divided by how much the volume is changing every second. So it'll be the total volume we have available from the cylinder divided by the flow rate that we've already calculated. And just to remind you, the flow rate that we found was 2 times by 10 to the minus 4 cubic meters per minute. So if you sub this into here, and then you sub this volume into here, you find that the burn time, when I convert it into a more ready unit, say days for example, is around 7,100 days. Excellent! That means that I don't have to worry about coming into the lab overnight to replace a cylinder when it's run out. Fantastic. In fact, this is such a long time that, remember that this flow rate was just a lower bound in order to make sure that we didn't melt the container. So what we could do is easily increase the flow rate by about a factor of 10, for example, because 700 odd days, 2 years, that's still plenty of time. Anyway, now that that calculation is complete, we're ready, we're done, and I can now present to you the finished design for the Desiccator. Thanks for watching. With the design of the Desiccator now complete, all that's left is to wait for the components to arrive and then get started on building it next week, so we can finally prepare our samples of analog Phobos regolith. The journey is just getting started. Be sure to subscribe so you don't miss it, and until then, I'll see you next time on Project PhoboCam.